Breaking barriers, Rosatom's groundbreaking plasma rocket technology set to slash Mars journey to just 1 to 2 months. On February 10, 2025, Rosatom, the Russian state atomic energy corporation, announced a significant breakthrough in space propulsion technology with the development of a plasma electric rocket engine. This innovation promises to drastically reduce travel time to Mars, potentially allowing spacecraft to reach the red planet in just 1 to 2 months as opposed to the nearly year-long journeys typical with conventional propulsion systems. Overview of the plasma rocket technology. The core of Rosatom's new propulsion system is a magnetic plasma accelerator. Unlike traditional rocket engines that rely on fuel combustion, the plasma rocket operates by accelerating charged particles, specifically electrons and protons, through a high-voltage mechanism between two electrodes. This process not only generates thrust but does so at unprecedented speeds. With the engine capable of expelling particles at velocities up to 100 km per second, approximately 62 miles per second. Key features. 1. Engine design and functionality. The engine achieves an average power output of 300 kilowatts and can produce a thrust of around 6 newtons. This thrust level is significant for interplanetary missions, enabling smoother acceleration and deceleration phases during travel. 2. Safety and efficiency. One of the most critical benefits of reducing the journey time to Mars is the enhanced safety for astronauts. A shorter mission duration minimizes their exposure to harmful cosmic radiation, which increases during prolonged spaceflights. Alexei Voronov, a senior official at Rosatom, highlighted the health risks associated with traditional space travel durations and emphasized how the plasma engine could pave the way for safer missions. 3. Testing and future development. A laboratory prototype of the plasma rocket has been created and will undergo rigorous testing. This testing will take place in a specialized vacuum chamber measuring 14 meters in length and 4 meters in diameter, designed to replicate the conditions of outer space. The team anticipates that a flight-ready model will be ready for testing by 2030, although initial launches will still utilize conventional chemical rockets for liftoff. For broader implications, beyond just Mars travel, the implications of this technology could extend to faster interplanetary missions and potentially voyages beyond the solar system. The advancements in propulsion technology could open up new frontiers in space exploration and colonization. Common themes across various reports. Multiple sources have reported on this groundbreaking technology, emphasizing its innovative nature and the potential to transform space travel. The reduction in travel time to Mars is consistently highlighted, along with the safety benefits for astronauts due to decreased radiation exposure. Furthermore, the commitment to rigorous testing and the careful development of this technology underscores the cautious but hopeful approach of scientists. Diverging points in reporting. While most reports agree on the fundamental aspects of the technology and its potential, there are variations in some details, such as the specific thrust capabilities and the nature of the testing processes. Some articles focus more on the theoretical implications of the technology, while others delve deeper into the engineering specifics. Future of space travel. The announcement of Rosatom's plasma rocket technology comes at a time when various nations and organizations are exploring new propulsion methods. Competing technologies include nuclear thermal propulsion and solar sails, which also aim to enhance the efficiency and feasibility of human exploration of Mars and beyond. However, Rosatom's approach, emphasizing the use of plasma propulsion, positions it as a unique contender in the race for advanced space travel technologies. Conclusion. Rosatom's development of a plasma electric rocket engine marks a significant advancement in the quest for faster and safer space travel. With the potential to reduce the journey to Mars to just 1 to 2 months, this technology not only represents a leap forward in propulsion systems but also inspires a new era of exploration beyond our planet. As rigorous testing continues and a flight-ready model is anticipated by 2030, the future of interplanetary travel could soon look very different. This breakthrough may ultimately lead humanity closer to becoming an interplanetary species. opening up new possibilities for exploration and colonization across the solar system and beyond. The content discusses Rosatom's development of a plasma electric rocket engine that could revolutionize space travel by significantly reducing the time it takes to reach Mars. Here are the counterintuitive aspects identified in the content. 1. Speed versus safety. While one might assume that faster travel to Mars would be more dangerous due to high speeds, the technology aims to enhance astronaut safety by reducing time spent exposed to cosmic radiation. This juxtaposition of speed leading to safety challenges the typical notion that faster travel equates to higher risk. 2. Electric versus traditional propulsion. The idea that an electric propulsion system can achieve much higher speeds compared to traditional combustion engines is counterintuitive. Many might assume that combustion-based engines, which have been the standard for space travel, would inherently be more powerful. However, the plasma engine's ability to accelerate charged particles to speeds of 100 km per second represents a significant advancement over the 4.5 km per second maximum achievable with conventional engines. 3. Initial launch method. It may seem logical that a state-of-the-art propulsion system would be used from the moment of launch. However, the plasma rocket will not be used until the spacecraft reaches orbit, relying initially on traditional chemical rockets. This highlights a more complex approach to space travel that integrates both old and new technologies rather than a complete overhaul. For resource requirements, the notion that a spacecraft will not carry large amounts of fuel for propulsion but rather a small amount of gas in a cylinder for the plasma engine can seem counterintuitive. It suggests a shift towards a more efficient use of resources where less fuel is needed for propulsion once in space, which contradicts common perceptions about fuel logistics in space travel. 5. Long-term implications. The expectation that this technology could facilitate missions beyond Mars and even to other solar systems might seem overly optimistic given the current limitations of human space travel. However, the technology could theoretically open pathways that were previously deemed unattainable, challenging the notion of what is feasible in interplanetary exploration. 6. Testing and verification. Despite the promising nature of this technology, the absence of peer-reviewed scientific papers and detailed technical documentation raises skepticism about its readiness for practical application. This contrasts with the typical expectation that groundbreaking technology would be immediately backed by extensive research and validation. These counterintuitive points illustrate the complexity and potential of Rosatom's plasma rocket technology while challenging conventional assumptions about space travel and propulsion systems. The report on Rosatom's groundbreaking plasma rocket technology provides a wealth of information about advancements in space propulsion that could revolutionize interplanetary travel. However, there are several important aspects and implications embedded within the details that may be overlooked by many readers. 1. Potential for broader space exploration. While the primary focus of the report is on reducing travel time to Mars, the broader implications of this technology extend far beyond the red planet. The mention that interplanetary trips are likely to become much faster too suggests a paradigm shift in how humanity could explore the solar system and beyond. This advancement could enable missions to distant planets and moons which were previously deemed impractical due to long travel times. The significance lies in the potential for discovering new resources, understanding planetary environments, and possibly even searching for extraterrestrial life. 2. Safety enhancements for astronauts. The report emphasizes that shorter journey durations would significantly reduce the risks associated with prolonged exposure to cosmic radiation. This is a critical point that often gets overshadowed by the excitement surrounding technological advancements. Protecting astronauts' health is paramount for long-duration space missions. The development of a propulsion system that can cut travel time to Mars to just 1 to 2 months could make human missions to Mars not only feasible but also much safer. This safety enhancement could lead to increased public and governmental support for ambitious space exploration programs. 3. Energy efficiency and resource management. The engine's design, which allows for the use of a small amount of gas instead of carrying large quantities of fuel typically required for chemical rockets, represents a significant step toward resource efficiency in space travel. The fact that the plasma engine does not need to be strongly heated means that components will experience less thermal stress, potentially leading to longer-lasting engines and reduced maintenance costs. This efficiency is crucial for long-term missions and could also reduce the overall costs associated with space travel, making it more accessible. 4. Technological validation and testing challenges. The transition from a laboratory prototype to a flight-ready model by 2030 is a critical timeline that suggests rigorous testing and validation processes must be undertaken. Many readers may overlook the inherent challenges and uncertainties involved in this phase. The report mentions that the prototype will undergo extensive testing in a vacuum chamber to simulate outer space conditions. This aspect highlights the complexity of space technology development, where many prototypes fail to meet performance criteria during testing. The significance of this lies in the recognition that while the technology holds promise, it must first prove its reliability and safety through comprehensive testing. 5. Collaborative international landscape in space exploration. The report notes that other countries, including the European Space Agency and the USA, are also working on technologies to reduce journey times to Mars. This indicates a collaborative yet competitive international landscape in space exploration. Many readers may focus solely on the advancements made by Rosatom, but the interconnectedness of these efforts underscores the global interest in space travel advancements. The significance here is that international collaboration could lead to shared knowledge and resources, potentially accelerating technological development and enhancing mission safety. 6. Implications for future propulsion technologies. The development of plasma rocket technology may pave the way for further innovations in propulsion systems. As mentioned in the report, this technology could facilitate faster interplanetary missions and even voyages beyond the solar system. Readers may overlook the fact that such advancements could inspire a new wave of research and development in propulsion technologies, including nuclear thermal propulsion, solar sails, and other novel methods. This could lead to an era of rapid technological progress in space exploration. 7. Potential for commercial space travel. The advancements in propulsion technology could also have significant implications for commercial space travel. As private companies increasingly enter the space sector, the ability to transport people and goods efficiently to destinations like Mars could open new markets and opportunities. Many may not consider the commercial aspect of such technologies, but the economic incentives for faster, safer, and more cost-effective travel could drive investment and innovation in the space industry. Conclusion. In conclusion, while the announcement of Rosatom's plasma rocket technology is certainly exciting, the nuances and broader implications of this advancement are crucial to understand. From enhancing astronaut safety and energy efficiency to paving the way for commercial space travel and international collaboration, the significance of this technology extends far beyond the immediate goal of reaching Mars in record time. Recognizing these overlooked elements can provide a richer understanding of the current state and future trajectory of space exploration. 1. Innovative engine design and functionality. The plasma electric rocket engine represents a significant shift from traditional combustion-based propulsion systems. By utilizing a magnetic plasma accelerator, this engine can achieve speeds of up to 100 km per second, greatly surpassing the maximum velocity of 4.5 km per second offered by conventional engines. The design involves passing charged particles between two electrodes while applying high voltage, creating a magnetic field that expels particles, thus generating thrust. This advanced mechanism not only enhances propulsion efficiency but also opens new avenues for interplanetary travel. 2. Safety enhancements for astronauts. One of the most critical aspects of this technology is its potential to improve astronaut safety during space missions. By significantly reducing travel time to Mars to just 1 to 2 months, the risks associated with prolonged exposure to cosmic radiation are minimized. This is crucial for ensuring the health and safety of crew members on long-duration missions, addressing a major concern in human space exploration. 3. Comprehensive testing and development timeline. The Rosatom team is committed to rigorous testing of the prototype in a specialized vacuum chamber designed to simulate outer space conditions. The timeline for development includes the completion of a flight-ready model by 2030, with initial launches still relying on traditional chemical rockets. This structured approach to testing and development underscores the importance of ensuring reliability and safety before full-scale deployment of the new propulsion system. For her broader implications for space exploration, the implications of this plasma rocket technology extend beyond travel to Mars. It has the potential to facilitate faster interplanetary missions and could even enable human voyages beyond the solar system. By revolutionizing space travel dynamics, this technology could expand humanity's reach into the cosmos, paving the way for future exploration and colonization of other celestial bodies. The advancements in propulsion systems could inspire further innovations that enhance our capabilities in space exploration. 1. The V2 rocket program, developed during World War II by German engineer Wernher von Braun. The V2 rocket was the world's first long-range guided ballistic missile. It employed a liquid-fueled propulsion system that showcased significant advancements in rocket technology. The V2's success laid the groundwork for future space exploration and was pivotal in the development of rocket technology in both the United States and the Soviet Union after the war. 2. Project Orion. Initiated in the late 1950s, Project Orion was an ambitious plan by the United States to develop a spacecraft propelled by nuclear explosions. The concept involved detonating nuclear bombs behind the spacecraft to provide thrust, which could theoretically allow for rapid travel to Mars and other destinations in the solar system. Although the project was eventually abandoned due to technical challenges and concerns about nuclear fallout, it represented a groundbreaking exploration of propulsion technologies that could drastically reduce travel time in space. 3. NASA's ion propulsion systems. In the late 20th and early 21st centuries, NASA developed ion propulsion systems that use electric fields to accelerate ions-charged particles to create thrust. One of the most notable applications was the Dawn spacecraft, which successfully used ion propulsion to visit the asteroid belt and study Vesta and Ceres. This technology allowed for more efficient use of fuel and enabled longer missions with reduced travel times compared to conventional chemical rockets. Ion propulsion systems highlight the ongoing evolution of space propulsion technology. Much like the advancements seen with Rosatom's plasma rocket technology. Future outlook: Rosatom's groundbreaking plasma rocket technology. The development of Rosatom's plasma rocket technology is poised to transform space exploration significantly. With the potential to reduce the journey to Mars to just 1 to 2 months, the implications for human space travel and interplanetary missions are profound. Here are several key predictions regarding the future of this technology and its broader impact on space exploration. 1. Accelerated Mars missions. By leveraging the plasma rocket's capability to achieve speeds of up to 100 km per second, future Mars missions are expected to be more frequent and ambitious. The reduction in travel time will not only enhance the feasibility of crewed missions but will also allow for more extensive exploration of Mars, including potential colonization efforts. Space agencies and private companies could plan multiple missions within a shorter time frame, leading to a rapid accumulation of knowledge and resources on the Martian surface. 2. Enhanced safety for astronauts. One of the significant benefits of the plasma rocket technology is the reduction of exposure to cosmic radiation. Longer missions expose astronauts to higher levels of radiation, increasing the risk of health issues. By cutting travel time, this technology will likely lead to safer missions, making human exploration of Mars far more viable. As a result, we may see an increase in public and governmental support for human missions to Mars with an emphasis on astronaut health and safety. 3. Broader interplanetary exploration. The advancements in plasma propulsion technology could pave the way for faster travel to other planets in our solar system, such as Venus or the outer planets like Jupiter and Saturn, with the ability to reduce travel times significantly. Space agencies could initiate missions that once seemed impractical due to the long durations involved. This may lead to the establishment of more advanced research outposts on other celestial bodies, facilitating a deeper understanding of our solar system. 4. Innovations in spacecraft design. The implementation of plasma propulsion systems will necessitate new designs for spacecraft that can accommodate these engines. As engineers and scientists work to integrate plasma technology into spacecraft, we can expect innovations in materials, thermal protection systems, and energy management. These advancements may have beneficial spillover effects into other fields, including aviation and terrestrial transportation. 5. Commercial opportunities in space travel. With the promise of reduced travel times to Mars and potentially beyond, commercial enterprises may begin to explore the use of plasma propulsion for space tourism and cargo transport. Companies focused on lunar and Martian tourism could leverage this technology to offer quicker travel experiences. Additionally, cargo transport between Earth and Mars could become more efficient, opening new markets for interplanetary logistics and trade. 6. Potential for deep space exploration beyond the solar system. If successful, plasma rocket technology could serve as a stepping stone for achieving deeper space exploration. The ability to travel faster between planets could be the precursor to developing systems capable of interstellar travel. Concepts such as using plasma propulsion for missions to nearby stars like Proxima Centauri could transition from science fiction to a tangible goal within the next several decades. 7. International collaboration in space research. As countries recognize the potential of plasma propulsion technology, we may see increased international collaboration in space exploration efforts. Joint missions to Mars and beyond could become more common as nations pool resources, knowledge, and technology. This collaboration might foster a spirit of global unity in the face of shared challenges in space exploration. 8. Need for regulatory frameworks. The rapid advancement of space exploration technologies will necessitate the establishment of new regulatory frameworks. As missions to Mars and other celestial bodies become more frequent, international treaties and agreements regarding space traffic management, resource utilization, and planetary protection will need to be developed. These frameworks will be crucial in ensuring safe and sustainable practices in space exploration. 9. Education and workforce development. The emergence of new technologies in space propulsion will drive the need for a skilled workforce equipped to handle these advancements. Educational institutions will likely adapt their curricula to include more focused studies on plasma physics, aerospace engineering, and space law. This shift will prepare future generations for careers in the expanding field of space exploration. Conclusion. The development of Rosatom's plasma rocket technology represents a significant leap forward in our capabilities for interplanetary travel. As we look to the future, the implications of this technology are vast, promising not only to transform travel to Mars but also to revolutionize our approach to exploring the solar system and beyond. Continued investment in research and development coupled with international collaboration will be essential in realizing the full potential of this groundbreaking technology. The next decade may very well mark the beginning of a new era in space exploration, characterized by unprecedented speed, safety, and opportunity.